Hey everyone, and welcome to this explainer. We're jumping right into one of the most massive, yet honestly, least talked about infrastructure challenges of our entire generation. Look, we all know artificial intelligence is completely changing the game, right? It's fundamentally altering how we work, how we create, and how we solve complex problems. But behind all the magic of those sleek algorithms lies a very strict, uncompromising physical reality. Powering our new digital world requires an absolute ocean of electricity. So today, we're going to unpack the hard physical limits of our electrical grids and figure out exactly where the power for this AI revolution is actually going to come from.
Okay, let's dive into this. To really get a grip on the massive scale we're facing, just look at this staggering statistic. Sam Altman, the CEO of OpenAI, recently pointed out that generating a single prompt on ChatGPT consumes about the same amount of energy as running your home oven for one full second. Now that might not sound like a huge deal at first, but think about it. Millions of people are querying these systems every single second of every single day. If we suddenly demand our electrical grids to support thousands of times more energy than our home ovens currently use, well, our existing infrastructure is literally going to collapse.
Now you might be thinking, hey, won't AI chips just get more efficient over time? And yes, for sure they will, but that brings us to a super fascinating concept called the Jevons paradox. Historically, whenever a technology becomes cheaper and more efficient, we don't actually end up using less energy. We end up using exponentially more. Think about cars for a second. Modern engines are vastly more fuel efficient than the ones from a century ago, right? But because driving became so much cheaper and easier, we drive far more often, completely multiplying our total fuel consumption. AI is following that exact same curve. As it gets smarter and cheaper, we're going to integrate it into literally everything, which sends energy demand straight through the roof.
To put this surging demand into real-world perspective, let's look at the massive data centers being built right now just to house these AI systems. A standard new AI data center isn't just pulling a few megawatts anymore. Tech giants are planning facilities that demand up to 1 gigawatt of power. To translate that into human terms, 1 gigawatt is enough electricity to power roughly 2 million homes in real time. That's a whole city. And remember, unlike your typical house that sort of powers down and sleeps at night, these AI servers are running at 100% capacity, 24 hours a day, 7 days a week. So the big question is, how on earth do we feed this hungry new machine?
Section 1. The Energy Trilemma.
So to figure that out, we have to understand the strict physical framework that grid operators are dealing with every single day. The crucial point here is that any modern electrical grid must perfectly balance three competing forces. It's like a giant puzzle. First up is sustainability. We absolutely need energy that doesn't emit greenhouse gases or pollute the air. Second is stability. The grid has to guarantee an uninterrupted 24/7 supply of power because modern society, and especially AI, literally cannot tolerate blackouts. And third, affordability. The energy has to be produced at an economic cost that regular citizens and businesses can actually pay. Finding an energy source that perfectly hits all three, well, that's the holy grail.
Section 2. Renewables.
Let's start by looking at solar and wind power. Now, renewables are fantastic for one very specific, very awesome reason. The fuel is completely free and inexhaustible. Sunlight and wind don't cost a dime, and when they're actively generating power, their emissions are basically zero. But there is a massive physical trade-off here. They are incredibly variable and strictly weather-dependent. When the sun goes down, solar production instantly drops to zero. When the wind stops blowing, the turbines stop turning. And actually, if the wind blows too hard, they have to shut the turbines down just to protect them. This wild, unpredictable variability puts extreme tension on grid operators who have to perfectly match supply with demand, literally second by second.
And here's the fundamental physical reality that makes all that variability such a huge headache. The electrical grid operates almost entirely on real-time demand. We just don't have massive grid-scale battery systems capable of storing a whole country's power for days at a time yet. You can kind of think of the power grid like a massive, high-speed highway that has absolutely zero parking lots. Every single electron produced must be immediately consumed. So if your massive AI data center needs power at 2 a.m. on a perfectly still windless night, renewables simply cannot step up to provide it. Because we lack that large-scale storage, the grid relies really heavily on fast-acting backup power to jump in the very second those renewables dip.
Section 3. Natural gas.
Right now, our main backup is natural gas. Now, what's really interesting about this data is the stark contrast in environmental impact. Gas is very often sold to us as a cleaner fossil fuel. And hey, compared to coal, which pumps out a massive 840 grams of CO2 per kilowatt hour, gas is definitely better.
sitting at around 480 grams. But take a look at renewables and nuclear all the way down there at just 12 grams. Claiming gas is clean just because it's better than coal is kind of like saying a massive fast food burger is healthy just because you didn't eat 2 of them. It totally fails the sustainability test.
But see, natural gas is highly valued by grid operators for a very specific reason. You can spin a gas plant up or down in a matter of minutes. It acts as the perfect shock absorber for those exact moments when a cloud rolls over a solar farm. However, the trade-offs are pretty steep. Aside from the obvious CO2 emissions, the entire extraction and transport process leaks methane, which is a greenhouse gas incredibly more potent than carbon dioxide. On top of that, because gas is an imported, highly volatile commodity, relying heavily on it drives up everyone's monthly electricity bills.
Section 4. Nuclear Energy.
Which brings us to our final pillar. And wow, there is a massive gap between public perception and physical reality when it comes to this one. When a lot of folks hear the word nuclear, they instantly think of outdated 1950s technology, picturing the tragic disaster of Chernobyl. But modern nuclear engineering is fundamentally a different beast. For instance, Chernobyl didn't even have a containment building. Today's commercial reactors are encased in massive, deeply engineered containment structures built to withstand extreme internal and external disasters. The physics simply do not allow a modern commercial light water reactor to explode like a bomb. Due to the low enrichment levels of the fuel, it is mathematically impossible.
When we strip away the myths and just look at the physics, the objective trade-offs of nuclear power become crystal clear. On the plus side, it completely aces sustainability and stability. We're talking massive amounts of firm, stable power 24/7, rain or shine, with lifetime emissions as remarkably low as wind and solar. But the downsides, affordability and time. Building a traditional large-scale nuclear plant is insanely expensive upfront, and the projects almost always get bogged down in decade-long construction delays and really strict political red tape.
But here's where things get exciting. The nuclear industry is undergoing this huge Henry Ford-style manufacturing pivot to solve those exact problems, introducing what are called small modular reactors, or SMRs. Instead of building a massive, custom, one-off facility on-site over 10 agonizing years, SMRs are designed to be mass-produced in a central factory. You literally build the reactor module, ship it out on a truck, plug it in, and when it needs refueling, years later, you just swap it out like a giant battery. This scalable approach could be the absolute game changer that finally solves the immense cost and timeline hurdles of traditional nuclear power.
Section 5. The Ultimate Comparison.
Let's move to a full synthesis and evaluate everything we've learned against the strict demands of the trilemma. This matrix brilliantly illustrates why energy is such a crazy, complex puzzle, especially when we compare the stability of renewable energy, natural gas, and nuclear energy, which is the core issue for AI. A super clear narrative emerges here. Renewables offer amazing sustainability, but their stability is fundamentally low because they rely on the weather. Natural gas gives us that highly dispatchable stability to balance the grid, but completely fails on sustainability. And then you have nuclear, which is the only baseload source that gives us both high sustainability and the constant 24/7 rock-solid stability that AI data centers demand, though it obviously struggles a bit with affordability. Bottom line, there is absolutely no single magic bullet.
Section 6. The Mix of the Future.
So how exactly are the world's most powerful technology companies navigating this harsh grid reality? Well, they certainly aren't waiting around for politicians to solve it for them. They are securing their AI investments right now. And this brilliantly illustrates a massive shift happening in the market. Big tech has realized that our traditional grid, which is totally reliant on variable renewables and polluting natural gas, just cannot support their 1 gigawatt AI dreams. So they're bypassing the grid entirely. Microsoft just signed an agreement to purchase 20 years of power from a restarted nuclear reactor. Amazon directly bought a massive data center co-located right at an existing nuclear plant. And consortiums of tech giants are pouring billions into accelerating the rollout of those small modular reactors we just talked about. They are literally voting with their wallets for firm, carbon-free stability.
When you step back and look at the objective consensus from actual energy operators, the roadmap for surviving the Jevons paradox and successfully powering our digital future is pretty clear. It requires a highly balanced mix. We must massively expand and upgrade our grid infrastructure, basically building wider electrical highways. We absolutely must maximize our use of cheap, clean renewables whenever the sun happens to shine and the wind happens to blow. But, crucially, to make it all work, we must maintain and expand nuclear power to provide that unshakable, 24/7 firm baseload. Doing that is the only way we can finally phase out highly polluting natural gas.
Look, the AI revolution isn't just some cool new software upgrade on your phone. It is quite literally the largest infrastructure build-out in human history. The energy has to come from somewhere, and the physical laws of our planet dictate that every single choice has a consequence. We simply can't run the future on magic. So I want to leave you with this final thought. Knowing what you now know about the strict, unforgiving realities of the energy trilemma, what real-world physical trade-offs are you willing to accept to power the future of human progress? Thanks so much for joining me on this